Hi everyone. In this video, we're going to go through section 28.2, the basic logarithmic form. In chapter 28, we're getting different methods of integration. We're seeing a little trig, a little logarithms, some e in the next section. Basically, what it boils down to is lots of practice with u substitution and seeing how we can evaluate more different types of integrals. So for this section, it is really important to remember that the derivative with respect to x of the natural log of x is 1 over x. The derivative of the natural log is 1 over x. So that means that when we integrate 1 over x with respect to x, we get the natural log of x plus c, right? Because those are opposites of each other. So derivative of log is 1 over x. Integral of 1 over x is natural log. But one additional piece to put in your brains here is that we have the natural log of the absolute value of x. So it's something extra that's tacked on that isn't there with derivatives. That's supposed to be an arrow there. And the reason for that is, remember the antiderivative is the area under the curve, and the curve 1 over x, it looks kind of like that. It has those two branches. So we have an area over here, right, that makes sense and there is area there. And we also have an area over here on the negative side, right? Both of those areas have value, have meaning, but the natural log of a negative number over here, it doesn't work. We don't take the natural log of a negative number is undefined. So we tack the absolute value symbols around there to give that area practical meaning and significance, because we can't take the log of a negative number. Now, in this next example, a word of caution, right? Let's look at an example where we integrate 1 over x squared with respect to x. Then we rewrite that with a negative exponent, x to the negative 2 dx. And then you add 1 to the exponent, negative 1, divide by the new exponent, negative 1, and it's negative, x drops into the denominator, negative 1 over x plus c. That's how we've been doing this integration all along. You bring your denominator exponents up with a negative. All right. Now, when you integrate 1 over x dx, if you use that same method, that same approach, x to the minus 1 dx, this is where you run into an issue. Add 1 to the exponent, you get x to the 0 over 0 plus c. And that does not compute. Dividing by 0, that is undefined. Okay, and so for that reason, when we integrate 1 over x dx, this has to jump out at you and shout, hey, I'm the natural log of x plus c. It's just you gotta just see it, and it's hard sometimes to see, but it's really, really important. X to the first power in the denominator, the integral of that is the natural log of x. Now we'll look at an example where we use a little u substitution, but first a note about how things are given. When we have fractions in an integral, sometimes they'll throw the dx up in the numerator, like in the book and in the test question or the homework question. And that, especially when the numerator is just 1, the dx will kind of take the place of that. So if you don't like the way that looks, it's perfectly reasonable to write this as 1 over 2x plus 3 and then dx after the fraction. All right. And now in this one, because there's more stuff in the denominator, there's a whole expression 2x plus 3. We're going to do this with a little u substitution. So we're going to say let u equal 2x plus 3, and then the derivative of u is 2. 2x is 2. 3 is 0 dx. Okay, so this u, this 2x plus 3 is right there. The dx is right there, but I don't have a 2 in my integral, so we write 1/2 divide by 2, du is equal to dx. So what that substitution looks like when it's done, you have your integral, 1 over u, and then dx is times 1/2 du. And if you would prefer, that 1/2 can just be written out in front of the integral. 1 over u du. So when we integrate that, we have our 1/2 again. 1 over u, 1 over x, that is the natural log of u plus c. Don't forget the absolute value symbols. Don't forget the plus c. And then when you take and back substitute what u is equal to, you get the natural log of, 2x plus 3, the absolute value of that, plus our constant c. Okay? That's the answer to that one. In this next example, we throw a little bit of trig at you. You might not even know where the natural log comes in, but we're integrating cosine over sine, which we could try to rewrite that as like cotangent, but there isn't anything that has that cotangent is the derivative of. We don't know that off the top of our heads. So for this one, we're going to use a little u substitution, and I will, if you see this on a test, I will clue you in that you should use this u substitution here. And the key to this one is to say, all right, we're going to let u equal what's in the denominator, the sine of x, and then du is the cosine of x dx. Cosine x dx is right there. That's my du. If we flipped it and set u equal to the denominator, it would be weird to have a du having a sine in the denominator. Like it wouldn't work out. So we start out letting u equal what's in the denominator first. Okay, so the denominator is u, so this is the integral of u in the denominator. And then cosine x dx is, I can write du up there, or if you don't like that, 1 over u du right there. All right, so that is the natural log of u plus c, and then we back substitute sine x plus c. And if you think about how that derivative would work, you'd have the derivative of the natural log, which would put the sine in the denominator, times the derivative of the sine, which is the cosine up in the numerator. Okay, so that all kind of checks out if you do the derivative. In our next example, we have another fraction with an x dx up in the numerator and a couple of terms down in the denominator. This again is one where we're going to use a u substitution. And again, we're going to set u equal to what's in the denominator, the couple of terms grouped together. And then the reason that works out nicely is when you take the derivative of u, the derivative of 4 is 0, the derivative of x squared, or negative x squared, is negative 2x dx. So we have this thing in the denominator is u, and then x dx is right there. That's the du almost. We just have this negative 2 to deal with, which we can divide by and have a negative 1/2 du is equal to x dx. Okay, so I'm dividing that negative 2 to throw it on the left-hand side. All right, now when we make our substitution, we're going to say this is equal to, in the denominator of my fraction, I have just a u, 4 minus x squared, and then the x dx is negative 1/2 du up in the numerator. If you don't like the way I wrote it there, put the 1 there, the du out there, and the negative 1/2 in front of the integral. That's another way to write it. If you don't like that, put the du there, put the negative 1/2 there. There's so many different ways to write this because these are all products. This is multiplication. The way that I prefer it personally when I write these down is to take that 1/2 all the way out in front of my integral. And then once again, I'm just integrating 1 over u du, which is the natural log of u plus c, and then back substitute ln 4 minus x squared plus c. And you can again check these with the derivative and see if you've done it correctly. In our next example, we throw one with an an exponential function at you. And because setting u equal to the denominator has worked out so well all along, let's do it again. U is equal to 1 plus 3e to the 4x. du is equal to, derivative of 1 is 0. 3e to the 4x, the 3 tags along. Derivative of the exponent is 4e to the 4x dx. That is 12e to the 4x dx. All right, I don't have a 12 anywhere inside of my integral, so just like in the other problems, we're going to divide by that. 1/12 du is e to the 4x dx. So that's how the u substitution works. This denominator is my u. The e to the 4x dx is 1/12 du. So when we substitute into our integral, I'm going to pull the 1/12 out, 1 over u du. Each of these problems, if you make the substitution correctly, boil down to a 1 over u du. So that is 1/12 natural log of u plus c, and then back substitute as we've been doing for a while now. 1 plus 3 e to the 4x plus our constant c. Now, of course, we get a nice little application problem here. We've got a question where we have to find the volume of a piece of tapered tubing, shown in figure 28.4, which can be described as the volume generated by revolving the region bounded by the curve, this guy, and the axes, I think that means like the y-axis, about the x-axis. Ultimately, let me zoom in on it here, what we're doing with this one. We've got, this is my region that I'm kind of focused in on, and it actually goes out to 2.5, although my graph only goes out to 1. So let's say 2.5 is out here somewhere. It gets a little bit closer still. Okay, this is getting revolved about the x-axis. And in doing that, in volumes of revolution, we want to think of this rectangular cross-section, this slice that we take out there. What shape does it make? It makes a disc as I revolve it around there. So this is the disc washer method that we saw oh so long ago. So we might need to look up a formula here and there, but fortunately you're watching the notes for this section, so I can give you the formula. V equals pi integral a to b f of x squared dx. Pi r squared is for that disk, pi times f of x squared. So v equals pi integral, our region here goes from 0 all the way out to 2.5, 0 to 2.5, and then my function is given to me 3 over radical 4x plus 3 to the second power dx. Then I will simplify this integral, 0 to 2.5. 3 squared is 9. The square root squared in the denominator is just 4x plus 3 dx. And now you can see maybe where the u substitution and natural log come in. Right? That 9 can get pulled out in front of the integral, but 1 over 4x plus 3, we let u equal 4x plus 3. du is 4 dx, so 1/4 du is equal to dx, right? We've seen this in lots of problems by now. So v equals 9 pi times the integral of 1 over u du, oops, I forgot my 1/4, times a fourth. If I could squeeze it in front of the integral, I would, but I'll leave it there for right now. Now, I have a bottom bound of 0. 4 times 0 plus 3 is 3. So I'm rewriting my bounds now. 4 times 0 plus 3. And 4 times 2.5 plus 3. 4 times 2.5 is 10. Oops, plus 3 is 13. So the new bounds of my integral are 3 and 13. Let's keep going here. So I'm going to factor out my 1/4, which I didn't before. So v equals 9/4 pi 1 over u, that is the natural log of u, evaluated from 3 up to 13. 9/4 pi natural log of times the natural log of 13 minus the natural log of 3. Okay, and that looks like a really ugly number. We could approximate it if we wanted to, but I could also use a property of logs, 9/4 pi, a difference of logs. We can write that as the natural log of 13 over 3. Whoops. And that's it. And the reason I dropped off my absolute value symbols was because I know the absolute value of 13 is 13, similar for 3. So that's the exact value there for the volume of that region. We could approximate it if we needed to. You could have used your calculator sooner. If this were a test type question, I would have you set up the integral and then just evaluate it in your calculator. That is the end of this section. Thank you very much for listening. Let me know if you have questions on any of the examples that I've done or on any of the homework problems. Have a great day.